Okay, now we will start the new topic, which is the design and cool down of cryogenic transfer lines. Okay. What is the plan of my talk? It's going to be something like this. We will introduce cryogenic transfer lines. And then when you talk about a cryogenic transfer lines, there is, first of all, you should realize that any transfer line will be almost similar to any cryogenic system. So always there'll be a heat transfer coming in from the ambient to the cold environment. So you need to protect it by having a suitable, insulation around it. So that means you have to have a vacuum jacket has to be surrounding the line which is carrying the cryogenic fluids. Okay, so because of the heat transfer coming into the transfer line, there'll be always a vaporization. And so you will have both the liquid and vapor simultaneously being transferred from the transfer line. That is, if you give 100% liquid also, it will go as some liquid and vapor part will be going in at the other end of the transfer line. Now, so you come across different type of flow patterns. That is how the fluid is flowing within the transfer line. You will have different flow patterns that will happen. Maybe something like stratified flow or bubble flow or wavy flow, or these are the different type of flows. Anyway, we'll see some of these things. Then there is a diagram called Baker diagram, which can be used for predicting what type of flow one expects, considering the velocity of the fluid, and velocity of the liquid, and velocity of the vapor. Based on that, you will be able to determine what is the type of flow that is going to happen inside a transfer line. Then when you have a transfer line, there is going to be a pressure drop because it's a pipe. So you have a pipe, then there is a pressure drop that will happen in the pipe. That means the inlet pressure will be some value, but the outlet pressure will be lesser than the inlet pressure. Okay, so there will be going to be a pressure drop by the transfer line, and we can estimate what will be the pressure drop in case it is a single phase type of flow. Single phase means there is only one, either 100% liquid or 100% vapor. That's the sort called single phase flow. And you can also have two-phase flow. That means both liquid and vapor can be simultaneously be present. Then it's called the two-phase flow. So you can think of two-phase flow pressure drop as well. Then we'll lastly talk about the cool down of a transfer line. How the transfer line cools down, how much time it takes for a transfer line to cool down. And there is a, for this, there is a detailed workout has been given in Randall Barron's book. I am going to present that here. I will try to present that here. And as simple as possible, I am trying to put it here. Let us see. Okay. Then we will discuss about how to design a transfer line. The rigid line or flexible transfer line, etc. We'll try to discuss. Of course, one can also find out the performance of transfer line by conducting experiments and so on. That may not be part of this particular talk. We may discuss about it later, and we'll conclude this talk. Okay, is that okay? Okay. First of all, what is a transfer line? A transfer line is a device which carries the cryogenic fluids. Okay, so it can be liquid nitrogen, liquid oxygen, or argon, whatever may be the transfer line, even liquid helium. The transfer line is a device which carries the cryogenic fluid, and it carries the cryogenic fluid from one location to another location. Okay. Now, this transfer line, for example, if I want to transfer, okay, let's take a common liquid like water. If you want to transfer water, what do? You take a pipeline and you apply pressure on one side. Then because of the increased pressure on the surface, then the liquid moves through the pipe, goes to the other side. Okay. Okay. This is a very, very simple arrangement for transferring of the cryogenic fluids. Okay. You can also use so-called buoyancy forces, and thereby you can transfer line. For example, you might have seen, suppose the water is available, water is there at a high upper level. You can use a pipe which is filled with completely water. And then if you insert the pipe such that there are no air bubbles present, then the water will flow continuously from the upper tank containing the fluid, I mean maybe water, to the ground level. This will happen till the water level reaches the same as the external level. After that, because there is no pressure difference, so it will not be able to flow. Okay. When you come to cryogenic fluids, as you know, there is going to be a lot of heat transfer. Because of the heat transfer, then there is a need to insulate the transfer line. So instead of having a single line, you will now have a line with a jacket. That means a tube in tube arrangement. That means two lines will be there. The inner line will carry the liquid. The outer line will be an enclosure which is having the insulation. It can be a vacuum insulation, or it can be a powder insulation, or it can be super insulation along with vacuum, etc. So the general concept of a transfer line is that you have a liquid carrying line surrounding which you have a vacuum jacket. Okay. That's the normal arrangement of a transfer line. Okay, as in any case, you will have to have appropriate bends or T-joints and various other things, or walls, safeties, etc., which will also be incorporated in the line. Okay, what happens when you have vapor? When you have vapor in the transfer line, it critically affects the carrying capacity of the line. For example, if I am transferring water, you may not have so much of water vapor bubbles will not be there so much. Okay, so almost the entire quantity what is passing through the line can be liquid. There can be small vapor bubbles, water bubbles, maybe air bubbles may be present along with the water. But when you come to cryogenic fluid, because of the heat transfer that is coming in, the line will now have large quantity of vapor. Okay, depends on the insulation. If the insulation is sufficiently good, then the number of vapor bubbles will be reduced. If the insulation is bad, then the liquid gets vaporized and you have large quantity of vapor coming along with that line. So the presence of vapor in the transfer line critically affects the carrying capacity of the line. So what you should do is, you should minimize the heat transfer that is coming into the line so that you will have maximum quantity of liquid that comes out. Okay. So the transfer capacity of cryogenic line reduces because of the mixture of vapor and liquid, and particularly having a lower density. Vapor has a lower density than that of liquid, and therefore if you get only vapor, okay, then you are not going to fill up the container which is the receiver. Okay. Now also what one should do is, in case you have large quantity of vapor, then you have to apply larger pressure for transfer, so which will lead to increased velocity. Okay, but sometimes this may not be always possible because the line may not be rated for such high pressures. That is one thing. Secondly, the joints, whatever you are making, may not be adequate, so it can give up at some places. Right. Okay. So how does one give an idea of what is the quantity of liquid that is transferred? So for that, you have to do an analytical prediction, and suppose even 100% you start with the liquid, because of the heat coming in, the liquid that comes out of the transfer line will be a two-phase flow. That means it will contain a mixture of liquid and vapor. Okay, and the analytical problem, this particular problem of how much liquid will be transferred, etc., is quite complicated, because there is always a continuous conversion of liquid to vapor because of the heat transfer. Automatically, this also changes it leads to pressure changes along the length of the line. Okay, liquid and vapor may not be in equilibrium, and this introduces other variables into the problem. And vapor phase can be, suppose a vapor phase is laminar, but liquid phase may not be laminar, or it may be laminar, we do not know. Okay, but even in spite of all this, description of this analytical problem is not so easy. Okay, and the pattern of flow also can be modified during the flow of the pipe. Okay, but what has happened is, experimentally people have studied, okay, the liquid vapor flow through pipes. Okay, it has been done for various several fluids, and from there, depending on the flow rate, velocities of the fluid flow, liquid flow and vapor flow, people are able to predict or able to say, yes, there are some distinctly seven distinct flow patterns are there in the fluid flow through the pipes. So this is what is, we call it as the distinct flow patterns. Okay, you can see here the fluid flow through a horizontal pipe. Okay, imagine a transparent pipe and the fluid flow is flowing, and then you can look at what sort of flows able to see in these pipes. So the seven type of this flows are like this: bubble flow, slug flow, plug flow, annular flow, stratified flow, dispersed flow, wavy flow. So the flow is always happening from left to right. This is on a horizontal pipe. Similarly, there are flow patterns also in a vertical piping when the liquid is flowing from the bottom to the top. Okay, that is normally the situation. You consider the liquid flow from bottom to top in a vertical pipe. Okay, and what about the bubble flow? The bubble flow is indicative of the maximum quantity of the liquid with the small number of vapor bubbles inside. So it's called a bubble flow. Suppose the heat transfer is a little increased, then the bubble flow, the number of bubbles, they can accumulate together, come together, and then you get what is called the slug flow. Then the plug flow is again, you have a in-between situation where you have pockets of vapor in smaller sizes. That is called the plug flow. The annular flow is a flow wherein the liquid is always tied to the periphery, whereas the vapor passes through the central core. That's called the annular flow. Okay, you can see here the annular flow, the liquid moving in at the periphery, and whereas the vapor is moving at the center. That's called the annular flow. Now, stratified flow normally happens at low flow velocities, where there is a very clear boundary between the liquid and the vapor. So you can see here the liquid is at the bottom part and the vapor is at the upper side. So the vapor is moving on the upper side and the liquid is moving at the bottom side, and they are well separated. This is normally occurring at low flow velocities, and this is called a laminar flow or stratified flow. Okay. Now, as you see, we are gradually increasing the vapor content of the system. Then you get what is called the dispersed flow or mist flow. The mist flow or dispersed flow is where you have large quantity of vapor and very small, less quantity of liquid, which are now the less quantity of liquid is in the form of bubbles. Okay. So therefore, liquid bubbles are now present, okay, in a flow of vapor. So this is called dispersed flow or mist flow. There is also another type of flow which is normally seen, which is called the wavy flow, in which the liquid flowing at the bottom side of the tube is in the form of a wavy flow pattern. So it's almost like waves moving along the liquid. So it is called the wavy flow. So these are the distinct flow patterns which have been normally observed in the horizontal fluid flow of the pipe. Okay. Now, these flow patterns can be described or understood by what is called a Baker's diagram. Okay. What is the Baker's diagram? We'll just have a look at that. Okay. It is there in the next slide. Okay. Now, the Baker's diagram plots two parameters. The parameter on the vertical axis is G by lambda. The parameter on the horizontal axis is L lambda psi by G. Okay, what is lambda? Lambda is rho G by rho A multiplied by rho L by rho W, and the whole thing to the power half. That is the square root of this value. Okay, psi is sigma W divided by sigma L. Okay, multiplied by rho L, mu L by mu W into rho W by rho L to the square whole to the power 1/3. So this is the value of psi. Okay. Now, what are these parameters? So we'll just have a look. Rho G represents the gas density. Rho A represents the air density, which is 1.2 kg per meter cube. And rho L represents the liquid density, and rho W is the water density. Water density is 998, so many kgs per meter cube. Sigma W represents the water surface tension, which is 0.073 Newton per meter. And sigma L is the liquid surface tension. You are considering some liquid, no? So whatever surface tension of the liquid. And mu L represents the liquid viscosity. Mu W is the water viscosity, which is 0.001 Pascal second. And L is the mass flow rate of the liquid. And the units here are pounds per hour, feet square. Okay. And mass flow rate of the gas is represented by G, which is again in pounds per hour, feet square. Okay. So if you look at these parameters, then you can see here for how the various patterns are described or distributed are shown here. So you can see for low flow velocities, etc., you can see stratified flow at the lower end. Okay. And above this, you have the wave. Okay. On the wave type of pattern, then still further up, you have annular flow, dispersed flow, slug flow, plug flow, and the bubble or froth flow. Okay. So these are the various patterns that are normally seen. So if you know these parameters, and so the Becker diagram has been prepared. If you know for a particular fluid, what sort of fluid velocity it has, what is its density, okay, what is the vapor velocity of the particular gas velocity, and what is the liquid velocity. And then if you know all these parameters, then you can determine what sort of flow you can expect through the pipeline. Okay. Okay, the Becker diagram essentially shows the liquid vapor velocities, and the quality factor determine the type of flow that will predominate. Okay. At relatively low vapor flow rates, the stratified flow occurs with very little interaction between the two phases. That means you have vapor is completely separate and liquid is completely separate. So there is a clear distinction between the liquid flow at the bottom and the vapor flow on the top. Okay, that is called stratified flow. Sometimes it's also called laminar flow. Now we keep increasing the vapor velocity, then you get wavy flow, then you get slug flow, then annular flow, then finally you get into what is called the mist flow or dispersed flow, becomes successively predominant. Now, at low quality of flow, that is vapor quality of flow, then bubble flow is very common, and the vapor bubbles will now reside within the liquid phase. And this is a type of thing that normally happens, where you normally get large quantity of liquid outlet. At the outlet, you will get large quantity of liquid. Okay. So increasing the fraction of vapor results in larger bubbles, and which then collect them to form plug flow. This is the general phenomenon what you have. Okay. So now there are similar flow patterns which are also present in the vertical flows. I'm not discussing that part here because I think it will be almost the same in all cases. Most cases it will be almost the same. So let us move on to what is called pressure drop in fluid. Okay. What is pressure drop? When a fluid is passing through a pipe, for the flow to occur, you have to have a pressure difference between the 2 points. So because of the pressure difference, the fluid is able to flow from one side to the other. Okay. Now, there is going to be what is called the pressure drop. That means whatever that is pressure on this side may not be exactly the same pressure on the other side. There is going to be a reduction in pressure, and this difference in pressure difference, this pressure difference is known as pressure drop. So this pressure drop can be estimated by various factors, and normally by this why this pressure drop occurs is because of the friction of due to the pipe friction for the fluid flow. And so it is the single phase pressure drop is normally estimated by the frictional pressure drop per unit length of the line, with the assumption that single phase flow is always occurring in the line. So what do you mean by single phase? Single phase means I am having only one particular type of fluid flowing through the pipe. That means either totally liquid or totally gas. So one phase of fluid is flowing through the pipe. That's what we call it as single phase. Okay. Now, the following expression is to be used for calculation of single phase pressure drop. It is given by delta P by delta L. Delta P is the pressure difference for a distance over delta L. You can call it as pressure drop per unit length, delta P by delta L. This value is equal to F, a factor F. F is called the friction factor, multiplied by m dot by a whole square. So multiplied by m dot by a whole square into 1 by, in the denominator, 2gc rho d1i. Okay. So what is all this? We will just see shortly. F is representing what is called the friction factor. Now the friction factor is the number which depends upon the friction to the fluid flow. So there are a lot of experimental studies which have been conducted for different type of flows, particularly varying the Reynolds number. Okay, and then people have arrived at the friction factors for different type of flows, either for a laminar flow or a turbulent flow or a transition region. The friction factor has been evaluated. The friction factor F is equal to 64 divided by RE when Reynolds number is less than 2300. In other words, you have a laminar flow type of flow occurring in the tube. Now, in case you have a turbulent flow, the value will be equal to 0.316 divided by Reynolds number to the power 0.25. For the Reynolds number range ranging from about 3000 starting point up to about 50,000. Okay, that is the upper limit for this. For this, use a formula F is equal to 0.316 divided by Reynolds number to the power 0.25. Okay, now if suppose the Reynolds number is greater than this 50,000, then you use a formula F is equal to 0.184 divided by Reynolds number to the power 0.20. Okay, so this is the way in which you calculate the friction factor. So obviously you can see the friction factor entirely depends on the fluid flow parameter, namely Reynolds number. What is Reynolds number? Reynolds number is given by rho Vd by mu. Rho is the density of fluid, V is the velocity of fluid, and D is the diameter of the pipe, and mu is the viscosity of the fluid. Okay. Now you can also express the velocity of fluid in terms of the volume flow rate. So if you take volume flow rate, then it is rho into q dot into 4 di divided by mu pi d1i whole square. So we are just expressing the velocity flow rate in terms of the pipe volume flow rate divided by the pipe cross-sectional area. So that's what we have been doing. So in this expressions, F represents the friction factor. M dot is the mass flow rate, that is expressed in kg per second. And then Q dot is the volume flow rate. Okay. And A is the cross-sectional area of the pipe in meter square. And you also have GC is the acceleration due to gravity. That is in meter per second square. And rho is the density of the liquid. So we are talking about the single phase fluid flow. So it's the density of the fluid, kg per meter cube. And D1I is the inner diameter of the inner pipe. That should be expressed in meters. and mu represents the viscosity of the fluid in Pascal second. Okay. So these are the various parameters which have to be incorporated. So obviously, you see, you can calculate what is single phase pressure drop for a particular fluid flow. So what you require is the friction factor. For that, you require the Reynolds number. Then you require the mass flow rate per, mass flow rate, and the cross-section area of the pipe, and the density of the fluid, all required. Okay, let's go on to two-phase flow pressure drop. See, for the two-phase flow pressure drop, that means two-phase flow means you have both the liquid and the vapor simultaneously moving through the pipe. So it is not possible to theoretically predict, but there are some empirical correlations at ambient conditions, and these are developed by Martinelli, Nelson, and Lockhart. Okay, and particularly for the frictional pressure drop, it is resulting from the two-phase flow through the pipes. So what are the assumptions that are made in these analysis for determination of two-phase flow pressure drop is, first of all, static pressure drop of liquid phase is equal to that of the vapor phase. That is number one. That is, the pressure drop of the liquid phase is the same as the pressure drop of the vapor phase in the static condition. Okay. Then you have the sum of liquid and vapor volume should be equal to the total volume of the pipe. Okay. Normally, these correlations may not be valid for slug or stratified flow. So, but other type of flows, yes, it is valid. So it is proposed that the two-phase flow pressure drop can be determined from the pressure gradient of either the liquid or the vapor phase, either the liquid phase or vapor phase flowing independently. Okay. So what is the formula for the pressure drop? So delta P by delta L for the two-phase flow is determined as phi square L multiplied by delta P by delta L for liquid flow. L means for the liquid flow. That means the two-phase flow pressure drop per unit length is determined. It is determined in terms of delta P by delta L of liquid. That is the frictional pressure drop per unit length for the liquid phase, it flowing independently. And the phi square L is an empirical parameter. So, okay, that's a parameter which you have to add to determine the two-phase flow pressure drop. Okay, what are these parameters? I think this table gives you a complete detail of these parameters. This phi L is equal to x square plus cx plus 1 to the power half divided by x. And what is x square? X square is CL by CV multiplied by Reynolds number for the vapor, REV, and Reynolds number for the liquid. So Reynolds number of vapor to the power m, Reynolds number of the liquid to the power n, and then multiplied by rho v by rho l. The whole thing should be multiplied by 1 minus x whole square, 1 minus x by x whole square. Okay. So this is the value for x square. Now, there are different values for all these parameters, the C, CL, CB, M, N, etc. All these parameters are available. And first of all, the value of C for different flow conditions are given here. Suppose the liquid is in the laminar flow type, and the vapor is also laminar, then the value of C is 5. So liquid is turbulent, then vapor is laminar, it is 10. Then liquid is laminar, vapor is turbulent, it is 12, etc. So both are turbulent, it is 20, and so on. Okay. So the value of C, the coefficient C, can be determined using these numbers. Then you also have the other parameters N, M, and then C for gas and C for liquid. Okay, so for all this, you can, C, G is nothing but C vapor. Okay, so these parameters again can be determined using this table given by the Martelli correlations. Okay, after getting these numbers, you can plug in and then calculate what is the single phase and two-phase flow pressure. Uh, now, let us first discuss about the transfer line cool down. Now, how does a transfer line gets cooled down? First of all, it is the transient nature of the cool down process can be exemplified by this figure here. So first, what happens? The cryogen starts entering the pipe, which is, let us say, a pipe. From the bottom, liquid is flowing to the top. Okay, initially it starts entering. Okay, liquid, as the liquid enters, it is a warmer transfer line. What happens? The liquid touches the transfer line, which is quite warm, and therefore it suddenly vaporizes and becomes superheated. So that's what is happening. Next, what happens? The pipe is subsequently cooled by the cold vapor, by the letting it absorbed by the evaporating liquid. As the increasing amount of liquid moves further down the line, so further down the line, more and more liquid starts moving in. Finally, the inner walls of the tube acquire the temperature of the cryogen, and now only liquid emerges at the exit. Cool down gets completed. So there are numerical studies have been numerous studies have been conducted to estimate the transient cool down period for the transfer lines. Okay, so here, for example, you get a vertical a picture is shown for the cool down of the transfer line. So what happens is the liquid starts entering here, it gets heated, okay, converts it to vapor, okay, superheated or subcooled liquid is enter here at the bottom. And then what happens, because of the lot of heat coming in, then the two-phase flow starts beginning. Then the boiling of the liquid happens here. And then the formation of permanent bubbles, or in other words, you call it a permanent flow. As you move upwards, here the bubbles now join together. That is coalescence of the bubbles happens. And then you arrive at what is called the slug flow. Then again, you get end of the slug flow. Then you have a plug flow. Then naturally what happens, you start entering and ending in what is called the annular flow. That means most of the liquids now you will be at the periphery and the center core is more or less a vapor. And then when it moves further outwards, then you have what is called only the mist flow. That means the liquid is now in the form of bubbles in small bubbles, and it is equivalent to having a wet vapor. And then at the topmost zone, you have a superheated vapor. So what you can see here is as the liquid starts moving upwards, it starts from the total liquid state to total vapor state at the other end. So gradually this thing keeps on proceeding further like this. And at the end, at the other end, you will get the stream of liquid and vapor. I mean, the temperatures keep on cooling down, and then this keeps on moving further out. And so more and more part of the pipe is becoming cooler and cooler. And that means the liquid starts wetting the pipe over a distance completely. So when the pipe is completely cooled down, then what happens? The liquid, what is entering at this end, gets completely, it completely becomes total liquid is seen at the outlet. So, but still there is going to be some heat transfer coming in, depending on the insulation, what is there on the pipe. So when there is even 100% liquid is entering at this end, the other end will have certain amount of vapor formation. In other words, there will be a finite void fraction for the liquid, emerging liquid. Okay. Now we are going to discuss the cool down time of a transfer line. So this is what we are going to talk about. Okay. How do you determine the cool down time of a transfer? So what we have to do is we take a particular section of a transfer line. Let's say the section 1 representing the inlet of the transfer line. Section 2 represents the outlet of the transfer line. For all our simplicity, we make the transfer line as horizontal tubes. Okay. So outside you have what is called a vacuum jacket. So you can see the outer line, which is a vacuum jacket. In between the two is you have the super insulation or vacuum super insulation along with vacuum or without vacuum, along with insulation, super insulation with vacuum or just vacuum alone. That sort of insulation may be present. Now the liquid is entering from the inside, from the left end, and liquid is going out at the outer end. That is because of the heat influx, both you will have a liquid and vapor that is going out at the other end. Okay. Now, what we can talk about is, first of all, there is a dotted line you can see here. This dotted line corresponds to the sort of thermodynamic system what we are going to consider. So that is the thermodynamic system. Okay. Now, that dotted line is as close to the wall as possible, both at the left end, the right end, and the top, upper wall or lower wall, everything put together. That is your thermodynamic system. So what will be the condition? Initially, this condition of this will be total vapor, right? When suppose you open the cryogenic fluid to start with, initially it will be 100% vapor. But later on, after some time, when the system is completely cooled down, then you have 100% liquid or whatever percentage liquid that will be present. So at the end, the left end, you will have total fluid coming in. At the right end, depending on the heat input coming in, there will be some part of it will be liquid, some part of it may be vapor. So you can imagine, you can think that the mass flow rate at the left end is m dot fl, whereas the mass flow rate or m dot f1, the mass flow rate at the right end will be m dot g2. So this is f and that is g2. Right? Okay. So this is the type of flow that, I mean, this is what will be the flow from the left hand flow at the right. Okay. Now the pipe has got a certain, there is a pipe which is carrying the liquid, and that pipe has a certain mass. Okay. You can call it as the mass of the wall, okay, wall of the pipe. And then there is a heat coming in from the external source, and that is Q dot external. That is the heat flux which is coming. Okay, this is, so the left boundary is taken as 1 and the right boundary is taken as 2. Okay, what we are going to do is we are going to apply first law of thermodynamics. What does first law of thermodynamics says? Q is equal to, okay, it goes for two things. For if I apply a certain quantity of heat, that goes for one is to change the internal energy and another one is to do some external work. In this case, there is no external work done because the fluid enters from the left end and then going to the right end. That's all. So there is no external work. But what is happening is there is a change in the, so we are considering two conditions. We are considering the conditions when you have an initial state where the entire thing is totally gas. And then we are considering a final state, or in other words, you call it as a steady state, wherein now the entire pipe is filled with the liquid. Okay. So you have two states, initial state, which is vapor, and the final state, which is liquid. Okay. That's what we are going to consider. So what we notice is, so we are going to estimate what is the heat that is coming into the system. This heat will represent as Q. Q is equal to MSS U multiplied by USS, that is the mass at the steady state in the pipe, in the thermodynamic system, whatever we are considering, multiplied by the internal energy per unit mass, USS, in the steady state condition, minus mass at the initial condition into internal energy at the initial condition, which is M0 U0. This is the first part, change in the internal energy part. Then what about the enthalpy part? The enthalpy part is again, this whole thing of cool down takes place in a particular time called TSS. T is the time, T represents the time, SS representing steady state. So therefore TSS is the integral 0 to TSS. What about the one which is going outside? Outside, whatever goes is the gas part. So M dot G2. So its enthalpy is Hg2. because we are talking in the second, the outlet. So m dot G2 multiplied by H G2, which is, enthalpy per unit mass of gas flow. So it is actually HG2. We are integrating over the time period from 0 to TSS. So you have to multiply by dt for this. This is outgoing. Minus what about the incoming? Incoming part is the liquid part. So it is again same integral 0 to TSS m dot F1, which is the fluid entering into the system, mass flow rate of the fluid entering the system, HF1 into dt. So this is the thermodynamic, first law of thermodynamics has been applied for starting from an initial starting time to the steady state, to the time, up to the time where the pipeline reaches steady state. So this is what we are now applying. So the various parameters have been defined now. One is Q is the total mass. Q is the total heat transferred to the system. And M is the mass contained. M represents the mass contained within our thermodynamic system. Please understand that you have got a dotted line, which you have seen earlier. And this dotted line corresponds to the mass, whatever mass that is contained, that we are going to talk about. Okay, it is the mass contained within the system. U is the specific internal energy of the fluid in the system, USS. And then m dot G2 is the mass flow rate of the fluid outgoing from the system. HG2 is the enthalpy of the fluid leaving the system. TSS is the cool down time. M dot F1 is the mass flow rate of the liquid into the line, and HF1 is the enthalpy of liquid entering the line. So these are the various parameters which have been there. So we have just applied the first law, starting from an initial time where the entire mass is only vapor. Then afterwards, it reaches the steady state. So the time in between is your TSS, which is the steady state cool down time. Okay. What about the heat flow? The heat flow is Q. The Q is equal to integral 0 to TSS Q dot dt. Okay. That is, it is an accumulation of the heat transfer rate over a time period from 0 to TSS. So Q dot is the heat transfer rate, and that you integrate it over from the initial time 0 to the final time TSS. So that's it. Okay, Q. But it consists of two parts. What are the two parts? The two parts are, one is Q external heat load that is coming into the system, Q external, Q dot external into dt, that is TSS 0 to TSS integral. Okay, Q dot is external into dt. Then additionally, you got also what is called a cool down of the line. So in a steady state, to reach the steady state condition, we start with the warm-up pipeline. So the pipeline has to get cooled. So how do we calculate? That is the mass into specific heat into, okay, the change in temperature. Okay. So the change in temperature has to happen from an initial state temperature, which is room temperature, to a final temperature, which is at steady state. So therefore, it is sum of various components. So summation of integral, okay, m dot mw cw dtw, and that has to be integrated from the temperature initial value to the final value. In other words, here in this case, it will be that is amount of heat that is going to be lost by the material. So in other words, it is the heat that is going to be given to the fluid to vaporize. So therefore, we will write as integral TSS to temperature SS to temperature 0. Okay, that's what we are. So now we have here the value of Q. It is the heat flow, that is. So Q external is a heat transfer rate from the ambient surrounding. MW represents the mass of the solid portion of the line. There are a number of solid portions of the line. One is the inner line, wall bodies, maybe there are couplings and things like that. Okay. Then CW represents the specific heat of the solid portion of the line. So we are using for the external heat that is coming in, we are just using the formula MC delta T. That's all we are using. Okay. So let's see further. I have rewritten the same equation. The first equation I have rewritten here. Okay. Now, this is the part which I discussed already. 2 external dt, and then this is the heat flux which is coming by the for the cool down of the transfer. What we can do is the heat flux can be simplified in terms of an average value. Okay. So external heat flux can be taken as, you have to integrate it from an initial condition till the final condition of cool down. So for doing that, what we will do is, so what you can see is that this rate is going to be continuously varying with time. Initially, cool down rate will be very small. Then gradually, as it cool down rate will be keep on increasing, then it will be becoming a maximum value. So therefore, what you will see is that you have to average it over the initial condition and the final value. So we can simply take it as it is half of the heat flux cool down rate. This is the heat transfer rate for external heat transfer rate at the steady state of, that will be the maximum value multiplied by TSS. So this integral can be approximated as half Q dot SS into TSS. Okay. What about the heat flux of cool down? This one. What about second term? Here also we can write it as, replace this integral by an average value. So it is summation MW, the mass of various components, then average specific heat, and then it is from T0 minus TSS. T0 is the ambient temperature, TSS is the steady state temperature. So it is the value. So MCP delta T, we are now rewriting it this way. Okay. Now, what about MSS minus M0? That is the mass contained within your thermodynamic system at steady state. Okay. Minus M0, that is initial mass, which is only the vapor. That can be written as, okay, you can rewrite like this: 0 to TSS, integral 0 to TSS, m dot Fy, F1 into dt. So this particular part is equal to MSS. Okay, minus of m dot G2 dt, 0 to TSS. Okay. Here again, what we can do is this integral can be sort of averaged. Okay, what you can put an average value. The average value, if you do it here, then m dot Fy average value multiplied minus m dot G2 average value, whole thing multiplied by the time difference TSS. So we are just simplifying all our things because we do not know how to convert all these integrals. So calculate the integrals. We are making an average value in all cases. That's what we are doing. Okay. Also, we can show that the mean enthalpy of the system, you can write this as integral 0 to TSS m dot G2 Hg2 dt. This we can rewrite it as m dot G2 Hg2 average value multiplied by TSS. So we are rewriting all the terms in this manner. Okay. So what we are doing is we are going to write the whole thing in this manner. So whatever the expression we have here now, here you see here this expression. We are going to write this like this. MSS USS, the first term is remaining same, minus M0 U0 remaining same. This term is, we are rewriting like this. M dot G2 average value multiplied by TSS multiplied by Hg2 minus of M dot F1, okay, TSS multiplied by HF1 average value again. So this is what we are writing like. So this expression has been rewritten. Okay. Now there are some small simplifications which are done. Okay. So what you can do is you can rewrite, you can add some additional terms, etc. in this expression. So you can rewrite this and you can show, I mean, I think this, whatever I have written here is an explanation for that, what is given in the text. So we can rewrite this like this. Q can be written as MSS USS minus HF1 minus M0 multiplied by U0 minus HF1 multiplied by, and sorry, in brackets, plus M dot G2 into Hg2 minus HF1 TSS. That means the same expression of Q we have rewritten in this manner. Okay. Whether this is valid, whatever we have written is actually shown in these calculations. I think I'm not going into these details of these calculations, but it is fairly simple to understand how exactly this is done. Okay. So what I have done is I have done the reverse process. So I have written the equation given in the text, okay, and then converted it in this format. Okay, that's what I have done. So for example, this is the final expression given in the text. So if you expand it, you get this. Okay. And you can simplify this expression, and then you will show that this is equal to the original expression what we got for Q. Okay. So this is just to make it convenient. That's all. Okay. So our expression for Q, which is the heat coming into the system, is given by MSS. Okay. Sorry, 1 minute. Yeah. So we can write like this: MSS multiplied by USS minus HF1 in brackets closed minus M0 into U0 minus HF1 bracket close again. The whole thing is bracketed plus M dot G2 Hg2 minus HF1 into TSS. Okay. So this is the heat that is coming into the system starting from the initial cool down to the steady state. What is TSS? TSS is the steady state cool down time. Okay, the time to reach from initial zero, first level to reach the steady state. That is what is called the cool down time. Now let us look at the Q. Q has been already determined. Q has been written in terms of two parameters. Q consists of two terms. One is the actual heat transfer that is coming into the system. The second term is the cooling down of all the thermal masses. Okay. So now this is the total heat that is coming. So this is going to be used. The cryogenic fluid is going to take away all this heat, both the heat. And so therefore, you are going to equate this to this part. So we can write half Q dot SS into TSS plus summation of MW, CW average T0 minus TSS. Okay, if you do this, then this is equal to the right hand side, whatever that is written here. Okay, we can also make one more simplification. That simplification is, what about MSS? MSS means it is the mass of the fluid in the steady state. Okay, that is nothing but the volume of the fluid multiplied by the density of the fluid. Okay, so you can rewrite it as volume into density of the fluid. So we can write MSS as VSS into USS minus HF1 minus, again, same thing is also applicable for M0. So initial state is having vapor. So therefore, volume multiplied by rho times, that is density of gas. So into U0 minus HF1 plus mg2 average value, m dot g2 average value multiplied by hg2 average value minus hf1, whole thing multiplied by TSS. Okay. So you see TSS is occurring on the left side as well as on the right side. So bring all TSS. TSS is what we have to calculate, right? It is the time required for the transfer line to reach steady state. So we have to calculate that. So what we do is we bring all TSS to one side. So we'll take this term to the right side. So when you do that, and exchange sides, you do that TSS into, I'm writing this first term, m dot g2 average multiplied by hg2 average minus hf1. Okay, minus half of q dot ss. So this term is what is there on this. So TSS is multiplying all this. So equal to the other terms. The remaining terms here is this term is coming on this side, m dot CW into summation of m CW, CW average multiplied by T0 minus TSS. Then this particular term, V into V common, V taken out outside, V into rho SS multiplied by USS minus HF1 minus rho 0 into U0 minus HF1. So this is the way in which you write this expression. So what is TSS now? You have to just write the right hand side, divide by this particular term. That is, this term goes to the denominator. So we get an approximate value of the steady state cool down time for the transfer line if you are able to introduce all these various parameters. Okay. MW, as you know, it is the mass of the transfer line components, and the summation indicates that you have to sum over for various components. CW is the average specific heat. T0 minus TSS represents the average. It is the initial temperature and the final steady state temperature. That value minus V is the volume of that particular space through which then the density of the fluid in the steady state, its internal energy minus the enthalpy of the liquid at the entering, and then this particular term is the gas density multiplied its internal energy minus the enthalpy of the liquid at the entry, which is entering. The whole thing divided by the m dot G2, that is the whatever gas that is coming out outside gas flow rate. Okay, Hg2 average value minus Hf1 minus 0.5 times QSS, Q dot SS. So Q dot SS is the steady state heat load into the system. So all these parameters are known. So from this, we can determine what is TSS. Okay, I'll take a couple of more minutes to complete this topic. Then we'll take a break for about 5 minutes. And then we'll come back. Okay, for the design. Okay, see this expressions. I think if you go to Randall's Barron's book, he will give you all the details. So this the entire thing is taken only from Barron's book. So you can go through that book and then get all the more details on this one. The expression tells you that there is a minimum flow rate for cool down of the transfer line. That means if the flow rate is smaller than this minimum value, then the line will not get cooled down at all. The transfer line will not get cooled at all. So you require a minimum flow rate of cryogenic fluid to flow through the line. And that is given by m dot G2 should be greater than, m dot G2 should be greater than Q dot SS by 2 multiplied by Hg2 average minus H liquid. So this is the formula which has to be used. Okay. It tells you that there is a certain minimum flow rate for cool down. So the minimum flow rate for cool down is plotted here as a function of pipe diameter. The pipe diameter is from 20, 40, 60, 80 centimeters. And the minimum flow rate expressed in terms of kg per second. So it is in logarithmic scale here. You can see for liquid nitrogen, liquid oxygen, and liquid hydrogen. So for these diameters, you require this much minimum flow. For example, let's say I have a 20 centimeter pipe. So if I want to have a liquid nitrogen, at least it has to be something like 1.5 kg per second. If it is smaller than that, the pipe will not get cooled down. Further, there is also a maximum allowable flow rate for cool down. Okay. If you exceed this flow rate in the transfer line, then there can be a lot of stresses which can be generated in the line. So you need to have both the minimum flow rate, that is a certain minimum flow rate is required for cooling down of the transfer line. And also you cannot allow a flow rate beyond a maximum value. Okay. It will cause a lot of stresses. And here on the plot, you have the maximum flow rate divided by the diameter of the pipeline is given here. So it is kg per second in the denominator per centimeter. It is plotted as a function of ball thickness divided by the inside diameter. So that ratio has been plotted here. So as you can see here, that the maximum flow rate values also decreases with T by delta T by di. Okay. So this is the arrangement what you are seeing. We will now take a break for about 5 minutes. Is it okay? Hello? Rahul?
Yes, sir.
We'll take a break for about 5 minutes because we are going to talk about the design of cryogenic transfer lines in the next talk. Okay. What's the time now, according to you?
11:04.
Okay. So shall we be, so we'll come back by 11:10?
Yes.
Okay.
Is that all right? Take a break now. Hello.
Hello, sir.
You people are back. Shall we
Yes,
start?
sir. Yes.
Okay. Okay, welcome back. I am going to discuss with you now how to design a cryogenic transfer line. So what we have seen is the cool down time for a transfer line we have seen. So that involved some basic assumptions. Okay, and we have to define a thermodynamic zone. And then we are assuming that the initial condition is only vapor and final condition is vapor with the liquid. Liquid will be there at the entrance point and some amount of vapor will come out at the outer end. So we using certain basic assumptions of averaging all the various properties and so on, we were able to calculate what is the cool down time for a transfer line. Okay. There are a lot more theoretical works are available okay, in this area. But anyway, I mean, the one what I have described is given by in Randall's Barron's book. So it may be useful to you. Okay. Now let's design the cryogenic transfer line. I'm going to discuss to you about the theoretical background of how to design a transfer line. Okay. What are the basic considerations for designing a transfer line? First of all, you should know what is the type of liquid that is flowing through the transfer line. It's nitrogen, helium, argon, whatever. What is the liquid that is flowing through the line that you should know. Secondly, you should know the material for the fabrication of the transfer line, what material you should choose. Okay. See, whatever we are discussing here is also equally valid for the design of a cryogenic system as a whole. Okay. Now, as far as the cryogenic transfer lines are concerned, how long you are going to use the line? How much is your transfer? For example, are you going to use it continuously? What is the transfer distance? How far it has to be transferred? Can you make it in a single length or you require joints in between? Okay, what is the expected volume flow rate through the line? How much should be the volume flow rate? Okay, what is the allowable pressure drop? Okay, for example, I start with a certain initial pressure. How much is the pressure drop that the line can accommodate? What is the maximum pressure drop that is allowable for the transfer line? So what is the quality of flow? That means how much vapor content will be present in the at the end of the transfer line. Also, you should decide also on the insulation which need to be used. Okay, should it be only vacuum insulation or should it be vacuum with any other type of insulation like powder insulation, foam insulation, or it can also be super insulation. Okay. And you must also worry about safety aspects. And overall, the cost factor that is going to be involved in making the transfer. So like this, there are a number of design considerations in making a transfer line. Okay. Now, for the transfer line, let us start with the material selection. It is generally fabricated with a suitable material, which is quite compatible to the cryogenic fluids. Okay, see, everything, whatever I am discussing is equally valid for a cryogenic system. Okay, so a cryogenic system, and because cryogenic system transfer line is also a cryogenic system, so the transfer lines are generally compatible with a specific material which is compatible with the suitable with the cryogenic fluid. So the main important criterion is that material should not become brittle and it should withstand cryogenic temperatures. So what are the normal materials generally used? They are aluminum, copper, nickel, stainless steel, etc. And also glass for small sizes of transfer lines. You can think of glass, the one inner line carrying the cryogenic fluid surrounded by another line, which is serving as a vacuum jacket. So you can think of that. So what materials should not be used? The materials such carbon steels, molybdenum, niobium, they are not suitable for low temperatures. We have seen this already earlier also in the design of cryogenic systems. The carbon steels have a difficulty because they undergo a ductile to brittle transition below 100 Kelvin. So they are not suitable for use below 100 Kelvin. Normally, one chooses stainless steels because from the fabrication aspects, it is quite easier to do this. It is 304 or 30L, 304L, or the ones which are generally used for developing the transfer lines because of the easy availability and fabrication. Okay, these are things which are generally used. Let's start with rigid cryogenic transfer lines. So we are going to discuss about rigid transfer lines now. Okay. If you want to make a rigid transfer line, let's say we are going to choose for liquid nitrogen flow. We are going to use liquid nitrogen as the cryogenic fluid that is flowing through. Okay. We'll select the typical volume flow rate, either 10 liters per minute or 15 liters per minute. That's the volume flow rate that's going to go through the pipeline. So what we will do is for that, what is the selection of the inner tube diameter? What should be its thickness? What are the pressure drop? What is the heat load that is coming in? You know, all these things have to be estimated. So these are the various things that need to be estimated if you are going to design a rigid transfer. Okay. So first we should determine what is the inner tube diameter, the tube diameter through which the flow is going to happen. So the volumetric flow rate through the transfer line is directly proportional to the inner diameter of the pipe in which the cryogen gets transferred. That means smaller the diameter, smaller the flow rate, larger the diameter of the pipe, larger will be the flow rate. So volumetric flow rate through the line will be directly proportional to the inner diameter of the pipe through which cryogen is flowing. The smaller diameter transfer line suppose you use that, then what happens is there are occasions the smaller diameter pipeline will have certain amount of a lot of vapor generation because of the initial heat, initial cool down, you will have a lot of vapor generation because of the heat in leak, because the line has to be cooled. So that vapor which is generating will push back the liquid in the opposite direction, and therefore the liquid flow will be obstructed. Liquid flow will be obstructed by this vapor generation. Because the liquid flow is going to be obstructed by this vapor generation, you need to provide certain amount of holes, vent holes in the upper zones. I mean, not in the vacuum zone. After clearing the vacuum zone, you put some vent holes so that this vapor will go out of this. You understand, I suppose. That is, the pipeline will generate a lot of vapor. So after the vacuum part is over, there will be an open portion which will be there also in the line with carrying only which will have only the inner line. In that, you put certain amount of holes on the sides, peripheries, such that the vapor will escape and the liquid will flow and then enter into this. So this is something which is normally done. Okay. Suppose, let's say Q dot is the volume flow rate in liquid in liters per minute. Let's say that's the volume flow rate. Then the diameter can be determined using this particular formula. The diameter of the inner line will be equal to, okay, a factor multiplied by Q dot into 10 to the power minus 3 divided by 60, whole thing to the power half multiplied by 10 to the power 3 millimeter. Okay, so this is the, that is in units of meter. It's coming in units of meter, or if you want to convert in millimeter, you write it 1000 millimeter. The factor K1 is actually a constant which depends on the factors like this, depends on a parameter alpha, and then the velocity of the gas, velocity of the fluid, and then the temperature of the gas, and then the temperature of the liquid, etc. All these various terms you have to introduce. But anyway, I don't have to worry about all this. This value for liquid nitrogen is about 1.6 roughly. That's the value for liquid nitrogen. So you substitute this number. If you know the flow rate, what you have to allow through the line, volume flow rate. If you know, from there you can calculate the inner tube diameter. Okay. So I have done this here. So we will select a certain volume flow rate, let's say 60 liters per minute. So it will lead to approximately about 50 millimeter diameter of the pipe. Okay. 50 millimeter will be the diameter of the pipe, or 5 centimeter will be the diameter of the pipe. In this case, as you can see, it goes on increasing as like a square. Okay. It's a parabolic increase in the volume flow rate as a function of inner tube diameter. Okay, now what we have to do, we must find out what should be its wall thickness. Pipe dimension is fixed. The wall thickness has to be calculated both for the inner line and as well as the outer pipe. So the inner pipe will correspond to the pipe which is carrying the cryogenic fluid. The outer pipe is serving as a vacuum jacket. Next pipe. Okay. First of all these pipes are selected based on iron pipe size, which is IPS. So both the inner and outer pipe diameters are to be selected based on the sizes prescribed in IPS, because these are the standard pipes which are available, and you have to select the pipes based on this. Okay, the wall thickness can be determined based on ASME sections, B331.5 standard codes for pressure tubes. So, for example, wall thickness of the inner pipe will be N P D1 out divided by 2SA plus 0.8 times P. Here, N represents the factor of safety, and P is the operating pressure, fluid pressure, and that is in terms of Pascal. And D1 out is the outer diameter of the inner tube. D1 represents the inner tube, out is the outer diameter. So D1 out will be the outer diameter of the inner tube, and that is expressed in terms of meter. And SA is the allowable stress. Okay, depends on the material what you are choosing. So this is exactly the same formula what we have also used in the design of the cryogenic systems. Please remember this. Okay, so we are using exactly the same formula. Okay. This is as far as the inner pipe wall thickness is concerned. Okay. Normally, if you get some wall thickness thing, then you have to select a pipe which is quite suitable, which is the pipe wall thickness should be greater than this particular number, greater or equal to than this number. Okay, equal to or greater than this number. So that's a sort of pipe what you have to choose. Okay, what about the wall thickness of the outer pipe? For the wall thickness of outer pipe, you write it as T out is equal to N PA 1 minus nu square. Nu is the Poisson's ratio, nu square divided by 2E. E is the Young's modulus of the material. The whole thing should be 1/3. We have to multiply this by D1 out, which is the outer diameter of your pipe, the outer diameter of the inner pipe. This should be wall thickness for the outer pipe. Okay. So now for the inner pipe, you have determined the wall thickness. For the outer pipe, you have determined the wall thickness. So you select the pipes accordingly. Okay. I have done the job here for 10 liter flow rate, then 15 liter flow rate. So you have an inner pipe, which is 26.67 millimeters in diameter, and wall thickness is 1.65 mm, whereas the outer pipe is 60.33 mm in diameter and 1.65 mm wall thickness. So this is the wall thickness that have been chosen in this case. For a 15 liter flow rate, then the diameters are somewhat different because you are now larger flow rates. So therefore, inner pipe is 33.4, and the wall thickness is 1.65. And for the outer pipe, it is 73.03. Wall thickness is 2.11 mm. Okay, so this is the selection of pipes parts over. Okay, what about the pressure drops? Now the pressure drops, we are going to use exactly the same formula what we discussed earlier. First of all, for single phase flow, you can calculate the pressure drop. I am using exactly the same formula. Delta B by delta L is equal to F into m dot by A whole square multiplied by 1 by 2 GC rho L into dN. So all the parameters are defined here. So rho L representing the density of the liquid, D1N representing the inner diameter of the inner tube, and F will be the friction coefficients. Okay, and we know the frictional coefficient, we can also calculate using the values can be calculated based on the Reynolds number that we have done last time. We have seen in the same previous part, the frictional coefficient will depend upon type of flow that is occurring, either the Reynolds number below 2,300 or up to 50,000, 3,000 to 50,000 or beyond 50,000. So these values are already available for the fluid flow, and you have to substitute this number for delta P by delta. So for a single phase flow system, you can calculate the pressure drop in terms of Pascal per meter. For example, it is 56.95 Pascal per meter for 10 liter per minute flow rate. We are talking about the mass flow rate of liquid nitrogen flow, right? Please remember. And it is for a 15 liter per minute, the single phase flow pressure drop will be less, 35.01, because the diameter of the pipe is now larger. Okay. What about two phase flow pressure drop? For a two phase flow pressure drop, we are exactly using the same Lockat-Martellini correlations, what we have defined in the earlier section, and using all these parameters and using the same formulas what have been given earlier. We are using this, we are calculating this, and you find, for example, as you increase the void fraction, which means when you increase the void fraction, you get more and more vapor. That means void fraction increases the vapor content of the system, so the pressure drop will be higher. So, for example, the two-phase flow pressure drop starting from about 0.1, okay, void fraction, up to about 0.4, you find it is almost going, exponentially rising. Okay, two-phase flow pressure drop. Again, the two-phase flow pressure drop is increasing. Similarly, in the case of 50 liter per minute, but you can see here clearly the pressure drop for the two-phase flow pressure drop for 15 liter per minute case is somewhat smaller for the same void fraction. Here, for example, for the void fraction 0.4, it is around 5,500 or so. Whereas here, for the same 0.4, the value is around 9,000. Okay. So 9,000 Pascal per meter. The reason for this is one is a smaller diameter pipe, another is a larger diameter. So for larger diameter pipe, obviously the pressure drop is somewhat lesser. Okay. We have seen now, we have designed the pipe, we have seen the pressure drop. Next, we have to find out what is the heat transfer. Okay. So you have an inner pipe, you have an outer pipe. So there is going to be heat transfer occurring from the outer one to the inner one. So the heat transfer will be normally conduction, convection, radiation. So in this case, we'll consider vacuum insulation. If you take vacuum insulation around the inner pipe, it's not adequate. It's adequate in most cases, yes, of course. Normally useful for small transfer lines. What does this vacuum insulation eliminate? What sort of heat transfer it eliminates? It eliminates, for example, the solid conduction heat transfer, because it is there only at the ends. Okay, and then gaseous convection heat transfer, gas convection heat transfer. These two it is able to take care. Now heat is transferred across the annular space of the vacuum insulated line, mainly by only two methods. One is radiation heat transfer. It is from the hot outer vacuum jacket to the cold inner line. And secondly, there is gaseous residual gas conduction or gaseous conduction, that is through the residual gas in the interspace. So there are two heat transfers which are occurring in this. Okay. So now let us start with the radiation heat transfer. For radiation heat transfer, I think some of these formulas you might have seen already in the design of cryogenic systems. Okay. So we are not doing anything different. We are using exactly the same formulas here. So the radiation heat transfer depends on the temperature to the power 4 of the individual for the radiating and the receiving surfaces. It is multiplied by factor Fe, which is called the emissivity factor, and then a configuration factor F12, okay, and then the sigma, which is the Stefan-Boltzmann constant, and then multiplied by A1, which is the outer surface area of the inner tube, multiplied by Ta to the power 4 minus T fluid to the power 4, which is the radiation heat transfer. Radiation heat transfer will be it depends on to the power of 4, the absolute temperature to the power 4. Okay, so that's what you are seeing here. Now, A1 represents the outer surface area of the inner tubing, and A2 represents the inner surface area of the outer tubing. Okay, T1 and T2 are the temperatures. Okay, temperature of the outer side of the inner tube, and then T2 is the outer temperature of the inner side of the outer tube. Right. So these are the various parameters. Now, one can use completely vacuum insulation. That means there are no super insulation material additionally added in the system. You have only vacuum insulation. Then in that case, the emissivity factor turns out to be 1 by epsilon, 1 by F epsilon, 1 by Fe is equal to 1 by E1, A1 by A2 plus A1 by A2 into 1 by E2 minus 1. So this is only for vacuum insulation. Here, if you, on the other hand, if you have multi-layer insulation along with the vacuum, then the Fe changes like this. Okay, this term 1 by Fe is equal to 1 by E1 plus 1 by E2 minus 1. Okay, this represents, so 1 by E1 plus 1 by ES minus 1, and this represents the surfaces, emissivity of the surfaces. Okay, and then the effect of number of layers. So you have layers n minus 1, the n layers of insulation is there. So the effect is n minus 1 into 2 by say E2 minus 1. Okay, and then plus 1 by E2 plus A1 by A2 into 1 by ES minus 1. ES is the emissivity of the shield material. Okay. So you have to use this formula now with the multi-layer insulation, presence of multi-layer insulation. It is exactly same formula what has been used earlier also. Okay, it's the same formula. Okay, so we have you can calculate using this equation how much is the radiation heat transfer, right? Next, what we do is we calculate what is the gas conduction heat transfer. What is the gas conduction heat transfer? As we know very well, the gas conduction heat transfer depends on pressure only. Okay, because now you are in the molecular flow regime. When you are in the molecular flow regime, because you have a long mean free path, so the molecular flow regime, the heat transfer is directly proportional to pressure. Okay, so we can write like this: Qg is equal to some constant multiplied by the pressure, okay, that is the interspace pressure, into A1, the surface area of the inner tube, and then T2 minus T1, and T2 is a Warman temperature minus T1. So this doesn't depend on T2 over 4, it just directly depends on the temperature difference. Okay, so here again, the values of G and FA, etc. are given here. The values of G is given here. and the G involves FA, the term FA is given separately by this. Okay. So we can now calculate the gas conduction heat transfer in the system using this formula. Okay. Now you see, if you have a one tube surrounding the other tube, which is normally the case in the case of transfer lines, then the solid conduction heat transfer has to be estimated by this type of equations. It is given by Q dot is equal to 2 pi L into theta A minus theta F divided by ln R2 by R1. So this is the formula, which is a solid conduction heat transfer between one pipe of this type, the outer diameter to the inner diameter, etc. If you know, then you can calculate the solid conduction heat transfer. Okay. Now, I have done, for example, some sort of calculations on this. Okay, for the very particular, a selected case where we have 20 liters of liquid, 20 liters per minute of liquid cryogen flow, and we have chosen the outer diameter of the pipe. Outer diameter of the outer pipe is 101.6 millimeters, whereas the outer diameter of the inner tubing is 48.3 millimeters. And the length of the rigid transfer line is approximately 1 meter. And the bayonet length is about 0.27 meters. And we have 10 layers of multi-layer insulation with interspace pressure of 0.001 Pascal. So these are the initial parameters which are used. So using this parameter, we can calculate, for example, heat load through radiation. We are using the same formula. Okay, 0.15 watts. The unit is not written here. Oh yeah, it is written here. It's in watts per meter. So 0.15 watts per meter. And the free molecular gas conduction is 0.37. So total heat transfer will be around 0.52. The experimental studies have been quite good, and they show a value of about 0.54 watts per meter. Now, heat transfer through solid conduction is 7.61 watts. Okay. Whereas the experimental measurement is about 7.8. Instead of 7.61 here, experimentally it is 7.8. So many watts. And the total heat load, including this radiation and conduction, is 8.22. Experimentally, we find it is about 8.34. So the mass required to fill the line, that is 0.83 kgs, whereas experimentally it is measured as 0.95 kg. So you can see there is a very good agreement between the heat transfer, what has been calculated, and the heat transfer, what has been measured in the developed transfer. Okay, what about flexible transfer? How do we do this? We are going to use exactly the same formula. Okay. In this case, you have to determine the inner bellow diameter, particularly for the flexible bellow. So we are now going to consider the clear length, the clear diameter of the inner pipe. That's what we are going to consider. So the calculation of wall thickness of the inner bellows, what has been done is calculation of wall thickness of the inner and outer bellows of the flexible transfer line is similar to those used in the case of rigid transfer line. There are no equations available for the calculation of wall thickness for the bellow case. Okay, and because of which we are going to use exactly the same formula which are useful for rigid lines. So instead of bellow, for whatever that bellow, whatever wall thickness you want to calculate, it will be just calculated based on the rigid lines itself. Okay. The bellow is, when you expand, you will find it will have a larger length, right? That's what will happen. Okay. So using the same, equations what have been given, assuming it to be a straight line, equal to the bellow is expanded into complete straight line of the inner tube. Then inner bellow diameter is about 20.5. It's a case for 10 liters per minute flow rate. And the outer diameter of the inner bellow will be about 26.8, because you can see the bellow will have one lower end and one upper end. And the wall thickness of bellow is 0.5 mm. So similarly, in outer bellow, the inner diameter is 51 mm, and the outer bellow, outer diameter will be 62 mm, and same wall thickness of 0.5 mm. And similar calculation done for 15 liters per minute. Okay. Both are available here. We can estimate the pressure drops by certain formulas. Okay. These formulas have been taken from the supplier's data of bellows. Okay. So you find bellow has a single phase pressure drop of 406.19 Pascal per meter. That's for 10 liter per minute thing. And whereas for 15 liters per minute, it is only 72.01. Okay. So the single phase pressure drop is calculated. You can also estimate the two-phase flow pressure drop. Okay. And the two-phase flow pressure drop can be estimated by giving the void fraction values. And you will find that if you include the void fractions, so you find it almost raises exponentially. Okay, with the void fraction. The left-hand case is for 10 liters per minute, and the right-hand case is for almost 15 liters per minute. So these are the two different calculations which have been done. Now, the heat transfer, the bellow geometry is evaluated as follows. The bellow geometry is made of equivalent to that of a straight tube with the same surface area of the bellow. So convective heat transfer assumed to be the same as straight pipe. Convective heat transfer to bellow is expected to be higher compared to that of a straight tube. However, this has not been taken into account in the present calculations. And you can see here the comparison of the results of pressure drop and heat load on flexible and rigid transfer lines. So first, let us consider rigid transfer line pressure drops. Okay, outer diameter is given, and for 10 liters and 15 liters, the diameters are given. For single phase flow, it is 56.95 so many Pascal per meter, whereas the other case for 15 liters per minute, it is 35.0. Actually, the diameter is bigger, so the pressure drop becomes smaller. Okay. So also for two-phase flow, it is for a certain void fraction, it is 177.80. Whereas if you take 15 liters, because that pipe is now bigger in size, it is only 1016.78. Similarly, we can calculate also for flexible systems. Like rigid system, we can also calculate for flexible system. Okay. What about the heat transfer? Heat transfer part has been done here for an heat load for rigid transfer line and heat load for a flexible transfer line for 10 liters and almost 15 liters. We are calculating for uninsulated line or foam insulated line, vacuum insulated line, and finally the vacuum insulated line along with some 15 layers of multi-layer insulation. So you can see here gradually as you keep on improving the insulation, the heat transfer rates keeps on decreasing from 439.64, it goes to almost 0.25 so many watts per meter. That's all the heat transfer that is going to be there in the system. And in a similar way, you can also see here that the heat transfer in the case of flexible bellow, you notice in the case of flexible bellow, you have slightly increased heat transfer, essentially because the bellow is having a larger, longer length. Okay, and therefore its values are somewhat higher. Okay, I think I will conclude this design of the cryogenic transfer line. I would like to mention that the transfer lines should be designed with utmost care to achieve the maximum throughput from the line. The design of rigid and flexible lines are quite similar, and depending on the end application, appropriate insulation has to be chosen for the cryogenic transfer line. For example, if I want to have a fast cryogen transfer with a large quantity of liquid flow, then I should go in for super insulation material. And there are a lot of textbooks are available for the study. This is by Cryogenic System by Randall Barron, and then Thomas Flynn, and then R.B. Scott. There are certain books are there. All these things have to be chosen for getting a better understanding of the cryogenic transfer lines. I think this is all I have to say. I would like to thank you for your patient listening.